Hello again, students, and welcome to a new nugget on biomass for energy. Today we will have a look at what happens, or what might happen, during storage of biological material. Most of you are probably well aware of the fact that a compost built from wet organic material, such as food waste or grass clipping and such, will become warm. The reason for that is to a major extent the microbiological activity within. And the same thing applies when you want to store biomass for energy purposes. So we will have a look at storage from a few different points of view and work some examples. But first, why would we want to store the biomass at all? There are several reasons that we want to have biomass stored in the energy supply system. The first reason is, of course, that the energy supply in modern society simply may not fail. So, for a fuel-based energy system, there must be fuel available at all instances. Municipal waste is generated all year round at a relatively constant pace, while energy production and consumption are seasonal. Agro-biomass, like straw, is generated seasonally, but not necessarily at the same time as the peak energy demand. Now, biomass is per definition an organic substance composed of living cells. It contains all the nutrients and constituents needed to sustain life. All dead biomass is successively decomposed by organisms specialized for this. These organisms are known as decomposers and are mainly fungi and bacteria, and they will establish also in the storage. Putting it simple, the decomposers eat the biomass, and they do that because they need food to grow and to multiply, so the total amount diminishes, and their activity will generate heat. If that heat is not ventilated away, then will the temperature rise, and this may ultimately lead to a self-ignition. These phenomena cannot be avoided, but they can be slowed down. Not everything, though, is based on biological activity. Several volatile organic oils, like linseed oil, just to mention one, are apt to self-ignite under common conditions. The page here shows a warning from the fire brigade in Montgomery County in America. There are volatile components like terpenes in the resins from wood. Also, wet waste and agricultural materials may well self-ignite. I'd like you to download the paper Fire Hazards from Self-Heating at Composting and Processing Sites by Manchester and Bardos. You find the paper from the company website by clicking your way through the submenus Publications and Downloads. Then go to the bottom of the list and the paper will be number 26 from below. Talking about waste, there are techniques to prevent the problems with waste storage. Some of the most obvious problems when it comes to household waste are bad smell, rats and rodents, and other sanitary aspects. Several of these problems can be eliminated, or at least almost eliminated, if the waste is enclosed in plastic wrapping. So baling municipal waste is in many cases an attractive option. The study in the paper recommended here concludes that an airtight wrapping hinders the temperature increase in the material, since oxygen inside the bale will be depleted. And also will the wrapping prevent the spread of bad odors, and it will prevent leaking of pollutants to water. In the study, they also tested how the bales would burn. This is one important aspect, because to use household waste in the energy system, it must ultimately be fed into an incinerator. And since the plastic wrapping will not only prevent fire, but will also keep all the water in, will the material be very wet. So one crucial factor is the combustion properties. but the study concludes that the material is still well combustible. There are other problems too associated with the storing of biological material. In case the material is stored in a closed compartment for a longer time, like on a transatlantic cargo boat, then will the atmosphere in that compartment be depleted of oxygen. And the same thing happens if the material is stored in a silo. So entering a closed compartment where biomass has been stored for a prolonged time is really dangerous. There are also risks for allergic reactions, and then there are other things like bad smells, pathogens, rodents, and other sanitary problems. Some of these things are treated or at least mentioned in the Busy Plan Handbook, so you may want to repeat the most relevant text sections. Let us now have a look at one type of storage that is common in the supply system for woody biomass, and that is the roadside windrow. As I've said in an earlier nugget, is brash first left for some time spread over the felling site. That is to allow the needles and green parts to fall off and return their mineral content to the soil. Following that period is the material gathered and windrows are built at the roadside. The windrows are planned to allow good access for sun and wind, and they are covered with waxed paper as a rain protection. The material is then left in the windrow for 6 to 12 months, and effectively it dries during this period almost without any degradation at all. The reason is that the cells are not damaged, so the goodies, nutrients, minerals, and energy-rich fats and carbohydrates are all maintained behind the lignocellulose cell walls. And since the windrow is porous, is any heat that might develop from decomposer organisms effectively vented away. So there is almost no food and no real shelter for the decomposer organisms, but water is transported away. In this example, I have rounded off the numbers, but what I want to show you is not the details. I only want to show you the overall picture that what happens in the windrow is two things. First, does the quality of the material, as measured by the heating value, increase? And second, does the total amount of energy in the material increase? So the windrow is a crucial part of an efficient supply system for woody biomass. It works only for such materials that can be stacked in a porous structure, because the thing is to allow for sun and wind drying, and brash, tree stumps and things like that have the mechanical strength to maintain such a porous structure. But then there is a limitation to what can be achieved in the windrow, and the ultimate limit is set by the equilibrium moisture quotient. The moisture quotient is the content of water expressed on a dry basis. This is different from the commonly used moisture content, which is the content of water expressed on a wet basis. You may want to go back to the Bioenergy Terminology Handbook from FAO that you downloaded in the 4th nugget in Lesson 1 in this course. Let me try to explain. Wood is a porous structure made up from cell walls. The dry substance itself is basically only cell walls, and the cell walls have just about the same density independent of species, and that density is about 1,560 kilos per cubic meter. So different species will exhibit different porosities, and that explains the difference in dry density. Balsa wood, to mention one, has a dry density about 160 kilos per cubic meter, corresponding to about 90% porosity. In contrast, ebony wood has a dry density about 1,150 kilos per cubic meter, and that corresponds to a porosity only about 25%. Now, many of the mechanical properties of wood depend on how big a portion of the available pores are filled with water. And then this portion of the pores is simplest described as the ratio of water to the ratio of cell walls. That is the moisture quotient, or the moisture content expressed on a dry basis. But for us, energy people, is the wet basis value the most relevant. Having said that, we go back to the drying process in the windrow. No matter how nice the windrow is placed and oriented, the drying of wood at ambient temperature is still a very slow process. And it is, as you understand, depending on the surrounding. And since the windrow is outdoors, it will depend on weather and on climate. Ultimately, but that might take a year or so, depending on the diameter of the material, may the windrow approach an equilibrium moisture quotient. And this equilibrium can be computed. A simple equation for that is available in the Wood Handbook from 2010, Chapter 4. That chapter can be downloaded from ResearchGate, so do that. You will observe that the text and the equation uses only the moisture quotient as a measure of the moisture content in the material. So the result of your calculation is a moisture quotient. The reason is, as I just said, that the mechanical properties of wood correlate best to the moisture quotient. So do not forget to recalculate the value you obtain into a moisture content on wet basis. Now go on to take the second theory lecture. That lecture will tell you a bit about what happens or may happen in a pile of chips, and you will have to know that to be able to understand the homework.